Have you ever just stopped and wondered why some things in the world just happen? You know, a fire burns, an ice cube melts in your drink. It feels really obvious, but behind the scenes, there's this powerful set of rules running the whole show. And today, we're going to unlock those secrets.
I mean, really think about it for a second. You light a campfire, and as long as it has fuel, it just keeps going, right? It's got a natural, preferred direction. But you could stare at a puddle on a hot summer day forever, and you will never see it suddenly decide to freeze itself solid. So, what's going on here? What's the secret rule that dictates this one-way street in nature?
Well, chemists have a word for this, and that word is spontaneous. A spontaneous reaction is simply one that has a natural tendency to happen under a certain set of conditions. Now, here's a really key point. Spontaneous does not mean instant. It just means the reaction is favored to happen. It wants to go forward, even if, like striking a match, it needs a little push to get the party started.
So let's break this all down. First up, we're going to explore what it really means for a reaction to be spontaneous.
Okay, so what does spontaneous actually mean in chemistry terms? It's any reaction that, well, favors making products. Let's take that bonfire again. The wood and the oxygen, those are your reactants. And the universe, for reasons we're about to get into, has a strong preference for them to turn into ash, carbon dioxide, and water vapor, the products. It's the path of least resistance.
This brings up a really good question, though. If burning paper is spontaneous, why isn't the book on your shelf on fire right now? It's because even these favored reactions often need a little nudge to get going. Chemists call this the activation energy. It's like having to push a boulder over a small hill before it can roll all the way down. The heat from a match is just that initial push.
All right, so what actually drives a reaction to be spontaneous? Well, there are two huge factors, and the first one is something we're all familiar with: heat. In chemistry, we call it enthalpy.
Enthalpy change, which we call delta H, is all about how heat flows. Reactions that give off heat, like a fire, are called exothermic. Their delta H is negative because the system is losing energy. On the flip side, reactions that absorb heat and feel cold, like one of those instant cold packs, are endothermic. Their delta H is positive. And since things in nature generally prefer to be in a lower, more stable energy state, releasing heat, being exothermic, is a huge thumbs up for spontaneity.
But why is heat even released or absorbed in the first place? Well, if you zoom way down to the molecular level, it's basically a tiny tug of war. See, it always costs some energy to break the old chemical bonds in the reactants. But you get a big energy payoff when you form new, more stable bonds in the products. If the payoff from making new bonds is bigger than the cost of breaking the old ones, then overall you release heat. It's exothermic. But here's the thing. Being low energy isn't the whole story. Not even close. There's a second, equally powerful force at play here, and it's all about the universe's unstoppable trend towards messiness. We call it entropy. Entropy, or delta S, is really just a measure of disorder or randomness. And one of the most fundamental rules of the cosmos is that overall, entropy is always increasing. Things naturally move from a state of order to a state of chaos. I mean, think about it. Your bedroom never cleans itself, right? It only gets messier. That's entropy in action. Let's make this super simple. Picture a perfect crystal of ice. All the water molecules are locked in place in this beautiful, neat, ordered pattern. This is a state of very low disorder, which means it has very low entropy. Okay, now, let's say that ice melts into liquid water. Suddenly, all those molecules are free. They can tumble around, slide past each other. The system just got a whole lot more disordered. Its entropy has increased. And finally, what happens when you boil that water and turn it into a gas? Whoa. Now the molecules are just flying all over the place in complete random chaos. This is a state of maximum disorder, and because of that, very high entropy. And temperature totally amps this up. The molecules in hot water have way more kinetic energy, which means they're zipping and vibrating around much more frantically than the molecules in cold water. More random motion means more disorder, and that means higher entropy. Okay, so we've got these two competing drives, right? On one side, we have the drive to reach a lower energy state, that's enthalpy, and on the other, we have the drive for more disorder, that's entropy. Now it's time to bring them together and get the final verdict on what actually happens. This really is the central question. Which drive is stronger in any given reaction? Is it the push towards low energy stability, or is it the relentless pull towards more and more chaos? The winner of this battle determines everything.
And the answer, the concept that acts as the ultimate decider, is something called Gibbs free energy, or delta G for short. This is the one that matters. It brilliantly combines both the heat change, delta H, and the disorder change, delta S, which also gets multiplied by temperature. And the absolute, unbreakable rule is this: a reaction is spontaneous only if it releases this free energy. In other words, for a reaction to happen on its own, delta G has to be negative, period.
And this table basically puts it all together beautifully. Look at that top row. If a reaction releases heat and gets more disordered, well, both factors are favorable. The universe loves it. Delta G will always be negative, and the reaction is spontaneous no matter the temperature. Same for the bottom row. If it costs energy and gets more ordered, it's a double whammy. It'll never be spontaneous. But these two rows in the middle, that's where things get really interesting.
Let's zero in on those middle cases, the ones where enthalpy and entropy are basically at war with each other. Because in these situations, a third player comes onto the field to act as the tiebreaker: temperature.
Let's go right back to melting an ice cube. To get ice to melt, you have to put heat into it, right? So it's endothermic. That's a positive delta H, which, from an energy perspective, is unfavorable. But, like we just saw, a liquid is way more disordered than a solid, so that's a positive delta S. That's favorable. So we've got a standoff.
And this is where temperature swoops in to be the hero. Remember the T in that equation? At low temperatures, let's say below 0 Celsius, the unfavorable heat factor is just too strong. It wins. Delta G is positive and the ice stays frozen. But as you raise the temperature above 0, that T starts to multiply the effective entropy. The drive for disorder gets more and more powerful until, bam, it completely overcomes the energy barrier. Delta G flips to negative, and that ice has no choice but to melt. So, looking at our master table one more time, you can really see how it all comes down to these two middle scenarios. When heat and disorder are in conflict, temperature is the boss. It's the deciding vote. For something like melting ice, you need high temperatures to boost the power of entropy. For another reaction, like freezing water, you actually need low temperatures to make an unfavorable entropy change less important. Temperature is the key that can flip the switch. And all of this brings us to a final, much bigger thought. We've seen that this relentless increase in entropy is one of the most powerful forces in all of chemistry. So let me just leave you with this question. If the entire universe, from the smallest reaction to the largest galaxies, is always and unstoppably moving towards a state of maximum disorder, what does that tell us about its ultimate fate?